Welcome to the today's video lecture series. Today we are going to see about the concept of Kirchhoff's current law, that is KCL, and concept of Kirchhoff's voltage law, that is KVL, which comes under the course outcome 1, analyze basic electric circuits using circuit reduction, mesh and nodal analysis, under which the learning outcome 1.1 is explain the basic terminologies of DC and AC circuits, under which specific outcome 1.1.2 is to explain the concept of KCL and KVL. So this is the reference book. First we will see about the Kirchhoff's current law. So Kirchhoff's current law states that algebraic sum of the current entering into the junction or entering into the node is equal to the algebraic sum of the current leaving away from the junction or node. So this is said to be the junction or a node. Already you know that where all the branch elements meeting at a point is said to be the junction or it is said to be node. So here I1 current, I2 current and I3 current are said to be the entering current into the node, whereas I4 current and I5 current are said to be the leaving current away from the node, because depends upon the arrow mark direction. If the arrow mark is towards the node, then it is said to be the entering current. If the arrow mark is indicated in outward direction, then it is said to be leaving current. So according to the statement, algebraic sum of the current entering into the junction is equal to the algebraic sum of the current leaving away from the junction. And here the entering current into the junction are represented by the positive sign. Here I1, I2 and I3 are the entering current. So hence I am representing them with positive sign. So I1 plus I2 plus I3. Whereas the current I4 and I5 are the exit current from the junction or outgoing current from the junction. So I want to represent them by negative sign. So plus minus I4 minus I5, which is equal to 0. So from this equation, we define that, we state that algebraic sum of incoming current and outgoing current are equal to 0. So it can be also stated as algebraic sum of incoming current, that is I1 plus I2 plus I3. So these three currents I1, I2, I3 are incoming current. So algebraic sum of incoming currents is equal to the algebraic sum of outgoing current from the node, that is I4 and I5. So this is the statement of the Kirchhoff's current law. So we have to know that this Kirchhoff's current law is applicable only when there is a node or a junction. So next we will see about the Kirchhoff's voltage law or KVL. In Kirchhoff's voltage law, we have to know that it is applicable only when there is a closed loop in a circuit. So consider this is a circuit. So this is voltage source in the circuit comprising the branch elements as R1, that is resistor 1, R2, resistor 2, R3, resistor 3, and R4, that is resistor 4. So inside this branch elements, the current entering into R1 is to be considered as positive polarity, and current leaving from the R1 is to be considered with negative polarity. Similarly for R2. Current entering into R2 branch is positive. Current leaving from R2 branch is negative. Similarly for R3. Similarly for R4. Now I am assuming the current direction is in clockwise direction, that is I. So here, when the conduction path in the circuit takes from negative polarity to the positive polarity, that means the conduction path takes from lowest potential to the highest potential, that is said to be the voltage rise or potential rise. When the conduction path takes from positive polarity to the negative polarity, that means conduction path takes from highest potential to the lowest potential, then it is said to be the voltage drop or potential drop. So according to the Kirchhoff's voltage law, that is KVL, algebraic sum of the voltage rise. So there is voltage rises only one source, one element, that is the source voltage. Here it is said to be the voltage rise, and remaining are all other elements, branch elements R1, R2, R3 and R4 are said to be the voltage drop. So I can write I into, I is a common current in the loop. So I into R1 plus R2 plus R3 plus R4. That means algebraic sum of all the voltage drops. So voltage rise is source voltage alone in this circuit. So Vs equal to, so voltage drop across the resistor R1 is IR1. Voltage drop across the resistive branch R2 is IR2. Now the voltage drop across the resistive branch R3 is IR3. Similarly, the voltage drop across the resistive branch R4 is IR4. So this is the Kirchhoff's voltage law. So from this equation or from this expression, we can say that according to the Kirchhoff's voltage law, algebraic sum of the voltage rise is equal to the algebraic sum of the voltage drops in the closed circuit. So in this circuit, there is no voltage rise, hence it is written as 0. So all other elements are the drop elements, voltage drop elements. So it has been specified as voltage across the resistive element AB is VAB, AB terminal is VAB. Similarly, the voltage across the resistive branch element in the terminal BC is VBC. Similarly, the voltage drop across the resistive branch element in the terminal CD is VCD. Similarly, voltage drop across the branch element in the terminal DA is VDA. So all the drop elements equal to 0 since there is no rise element in the given circuit. So that is what it has been stated. In any closed loop network, the total voltage around the loop, the total voltage here it is said to be the voltage rise, is equal to the algebraic sum of all the voltage drops in the same loop, or otherwise we can say it as in the closed network or in the closed circuit, the total voltage drop or the voltage rise and the voltage drop and the algebraic sum of the voltage drop is equal to 0. So that is what about the Kirchhoff's voltage law. So I hope that you would be understood about the concept of the Kirchhoff's current law and Kirchhoff's voltage law. Thank you.